Getting into the final section of Chapter 7. This is Part 1 of Section 7. What you're seeing in this section here is really mostly review. It kind of puts the pieces together for the last couple videos with the first derivative test and second derivative test. One quick summary statement that I would make is, if you're trying to determine a stationary point like a local max or a local min or a point of inflection, you can use either test. You can use a first derivative test or a second derivative test, and in most cases it doesn't matter which one you use. However, what we saw in the last video was with the second derivative test, you can run into some cases where you get inconclusive results, and so because of that, you then have to do some extra steps or go back to a first derivative test instead. So as we kind of look down, this is a great summary statement of the process for doing the second derivative test that we covered in the last video. So remember with that, this is where all these cases would start. So here's kind of your key first step. If you're ever asked to identify stationary points of a graph and classify what they are, this is where that process begins. No matter whether you're doing the first derivative test or the second derivative test, we first have to identify the stationary points by setting the derivative equal to 0 and solving for x. It's those x values that we can identify as our stationary points. Remember, stationary points are any points that have a slope of 0 where you would draw a horizontal tangent line. So because of that, if the slope is 0, that means the derivative is 0. And so that's where this process begins. What we saw in the last video was if you identify your stationary points and you're trying to then figure out whether it's a max or a min or a point of inflection, the second derivative test works like this. If I can find the second derivative of the function, and no matter what value I plug in for x, it is always positive, then we know that that graph is concave up all the time, and therefore our stationary point would be a minimum point. If we look at the second derivative and our x values that we sub in are always negative, then we know that the graph is concave down, therefore the stationary point is a maximum. But here's a problem you run into with the second derivative test. If we can't identify whether the graph is concave up or down, it could be because it's a point of inflection, but we don't really know that for sure. What we saw in the last video is if the second derivative equals 0, well, then we could test a couple numbers on either side of this x value and see if we're getting a sign change. If I plug in a number to the left of this and to the right of this, and I get one positive and one is negative, then we can say, okay, well then it's a point of inflection. But what if the signs don't change? So what if we have a 0 in the second derivative and I test numbers on either side and either they're both positive or both negative? If you're not getting the sign change, then we don't know whether it's a max or a min or a point of inflection. We can't state any of that. And so this is kind of the one hang up with the second derivative test. So if that happens, we simply fall back on the first derivative test if you get a inconclusive result for a certain value within your second derivative test. This was the kind of the procedure process that we took, and again, you can identify this with the last video that we submitted here, so you can always go back to that one, but this is a pretty good little summary page of what we covered in that video. So and this is kind of your ending statement here that I was just referring to. But if you get an inconclusive result, well, then you fall back on the first derivative test, because really the first derivative test always works. So that's kind of the sure way of going. And remember, what we did with the first derivative test is when you identify your x values, so when you have a first derivative where it equals 0, you find your x's, which are your stationary points. You don't do the second derivative, you stay in the first derivative and you test numbers on either side of x to see what your graph is doing, if it goes from increasing to decreasing or from decreasing to increasing, or if it doesn't change at all. We know we had a point of inflection, but we use that first derivative test to identify what our stationary points are. So here's just kind of another example of what we're doing with this whole process. But again, if you're asked to find relative extrema, and again all that means is it's a stationary point, either a max or a min or a point of inflection. So these always start by finding your first derivative, setting it equal to 0, and then solving for x. And so in this case, we can see for this function that we have stationary points where x is 0, as well as where x is 6. Whenever we are asked to identify points, remember that means you need an x coordinate and a y coordinate. So at some stage in this, and I can either do it now or at the end of the problem, but at some point I'm going to need to plug these back into the original function to get y values to go with them when I identify the points. I need to state them as complete ordered pairs. But here's where the next step in this process went. So if we are working with the second derivative test, so we found the second derivative that you see here. I'm going to take, I'm just going to start working on this guy first, but I'm going to take a value of 0. I'm going to sub it into my second derivative and see what kind of result I get. You can see that I get a negative result at this point. So that means in that area of the graph, the graph is concave down, which means this is a maximum point. If I do the same thing for my other x value, so if I plug a 6 into the second derivative, I can see that it is positive, which means in this area of the graph it is concave up. Therefore, I would have a minimum value within that area at x equals 6. And so this is just that step of plugging those numbers back into the original function to get y values to go with them. One thing I wanted to show you within this problem is something you can do with your calculator. We did this by hand as far as just kind of solving for x and plugging them back into the original function to get y values. This is something you can do on a calculator, so I'm going to show you that really quick. So I went ahead and went into my y equals button right there. Then I threw in the function that we're talking about for this problem. So there it is right there. And then I'm going to go ahead and hit graph. One thing you might have to do with some of these graphs is if you go into your window, you might have to make sure that your settings are appropriate for the graph. So what I mean by that was if say for example, my y values were too small, I may not see the max or the min within that graph. And so sometimes you have to toy with your settings within your window. So real quick explanation on that, but if you look at your x min and your x max, so again, this is just what you want to see on the screen of your calculator from left to right. The x scale is what you want to count by. I just always count by ones on that. And then this is what you want to see on your window from bottom to top. And then that's the scale on that. So I had to toy with these numbers a little bit so that I could see a clear picture of my graph. But here's what you're going to come up with. I can clearly see that this is a local maximum and this is a local minimum. And if I want to identify what those values are, under calc is where you get most of the cool features for graph stuff. So I'm going to hit second calc. And for the first one, I'm going to choose maximum. So I'm going to hit max because I can tell just by looking at the graph that I have a maximum in this area. So my calculator is going to ask me a couple questions. I need to sort of zero in on this portion of the graph. So it's going to ask me to establish a left boundary. So I'm going to go to the left a couple times and hit enter. And now it wants a right boundary. So I'm going to go to the right a little bit and hit enter, and you can see the lines that just came up on my calculator tells me that my calculator is now going to give me the max within that area of the graph. And so whenever it says guess, just hit enter, and there we go. We have our maximum point. I know the value looks a little weird on this, but if you can interpret this properly, this is saying -2 point blah 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 times 10 to the -6 power. That's the same thing as saying 0. I don't know why the calculator doesn't just put a 0 there, but that's a 0. So 0, 10, I can see is the maximum point in that area of the graph. I also have a minimum, so if I go back into calc and choose minimum, and again, it's going to ask me the same question. So I know it's right about here, so they're going to ask me for a left boundary. So I'm going to go left a couple times and hit enter, a right boundary, hit enter. You can see the graph now zooming in on that portion of the graph to give me the lowest point or the minimum within that area of the graph. So if I hit enter, there you go. I got 6, -98 is a minimum of that graph. And so that's something we can take advantage of on our calculator for graphing. So let me go back to the main part of notes here. Again, if you would have looked at this function here, here's the case where second derivative doesn't work for you. So if you were to take this function, and if you start by finding the first derivative, which they used the chain rule on this, so that's something we worked on this chapter. But if I took the chain rule and found the first derivative and set it equal to 0, I'm going to find that my stationary point is at x equals -1/2. So I got one stationary point right here. If I find the second derivative, like you're seeing here, so if I find the second derivative, which is this guy, and I sub in that number, I get 0, which is inconclusive. So that might be a point of inflection, but we don't know for sure. I could test a couple numbers on either side of this and see what happens. But if I tested a number to the left of -1/2, like say -1, well, if I put -1 in here, because of this guy, I'm going to come out with a positive answer. And if I test a number to the right of this, say 0, and plug that in here, I'm also going to get a positive answer. There's no change in sign. So because there's no change in sign, I can't for sure say what this point is. I don't know how to classify it yet. So that's when you go back to your first derivative test, or you could have just done the first derivative test from the beginning, and I test numbers on either side of -1/2 within the first derivative, and then I can identify where if my graph is, so if this is my value at -1/2, if I use the first derivative test, well, any number to the left of -1/2 is going to give me a negative result. Anything to the right of -1/2 is going to give me a positive result. So I know that if my graph is going from decreasing to increasing, then I must have a minimum point in that area. For the last one that you're seeing here, this is just a little bit of vocab so you can see the difference between what we would call a relative max or a relative min compared to a global max or a global min. So this is the same graph that we were looking at up above, but let me just kind of show you the difference within the terminology. You can see that this point right here we would refer to as a maximum point, simply because it's the highest point in that area of the graph. However, it is not the highest point overall within the graph. This graph goes up forever towards infinity. So that's why we would refer to this as a local max, because it is the maximum point, but only within one area of the graph, right? Whereas I do have really a global max, we would have to say is either infinity, or you could say, well, you know, I can't really identify a global max because this graph goes on forever. So same thing with point B right here. We would see this as a local minimum because it is a minimum point only within one area of the graph. The graph over here goes down towards -infinity forever, so this is not the global minimum, it's just a local minimum. The global minimum on this would kind of come with the same explanation that this guy came with. It's heading towards -infinity, so you really can't establish a global minimum. But if you take the same graph and establish some boundaries for it, so now we are cutting it off at -2 and +10. So now you can see right here it does not go on forever. We cut off from left to right where it can go. So now I can establish point A as a local max and point D as the global max, because D is the highest point overall on the entire graph. Same with point B. Point B here is a global minimum because it is now the lowest point on the entire graph overall.